Okay, any questions before we get rolling? Okay, so let me remind you all the last thing that we did. Let me get before you just roll. If we have, let me see, we can go small, okay. So we proved this in kind of a general setting last time, that the degree of K over F, degree of K over E, times the degree of E over F. This is, of course, this is the most useful, I guess, when you're looking at in finite set, but this is true for infinite extensions as well. So sometimes you might want to distinguish between a countable and an uncountable extension. Okay, so let me introduce a little bit of terminology here. Let F be field and X a subset, and we need a subset. Then we might say the subfield of F generated by X generated by X is, I'll call it something. So it's just the intersection of all subfields that contain X. Let me also make another distinction here. Now let F be a field, and let's say that X is some finite set. So this is just a finite collection of some garbage that you find in F. Then okay, so here's kind of the setup here. I've got a field F, big field. Then I've got a smaller field K contained in there, and then just a collection of other things, some flotsam and jetsam, A1 up to AN that I find in F. Then K is the smallest ring containing well, actually, let me say subring of F, although whatever Brooks subring of F containing K and X. Notice that that's kind of a polynomial bracket notation. And what this is this is the set of F, A1, A2, AN, where F So here's the way I like to think about this. This is the smallest ring that contains K and all these elements here. Okay, so what does it mean for a ring to contain K and a bunch of elements? What do you got to contain? You got to contain all products, all powers, all sums of these elements and K. And so basically, that's why this works, right? Basically, this is a set of all outputs that you can get from plugging in these elements of X into a polynomial named variables. So in particular, so the smallest ring containing K and the element A is just plugging in for one variable. Right? On the other hand, let me introduce you to another notation. This is the smallest subfield of K of F containing K and X. And how about this? These set polynomials, what do you think I'm gonna do here? Think rationally. I bet you'll come up. How about rational functions, right? That's right. So, because basically the smallest field containing these things should contain the smallest ring containing this, right? And in fact, it should be the quotient field, so it should be all fractions. So let me be a little bit careful here. This is where F of X1, X2. Well, actually, let me write it this way. It will probably be better for me to write it this way. Over Q, where P, Q are polynomials, and Q of A1, A2, AN is 0. So in other words, this is basically plugging in all the values A1 up to AN into all possible rational functions as long as your denominator is not 0. And in particular, so KA is the set of P of A, Q of A, Q of A, P, Q, AX, and Q of A. Here's a more terminology that I might use, and I guarantee I'll use it. If then A is all and simple. and you see why it's called simple, I guess, because you only need one element to generate it, right? In the sense that, right, so you only need one element to make the smallest field that contains K and A. I will also note that you can extend this in a very natural fashion to an infinite set, right? Not just the finite ones here. And finally, if M and F are subfields, field F, then the composite of L and M, and this is often written LM, is the subfield of F generated by L, B. So if you just take everything in L and everything in M, see what they generate. So in other words, the composite is it is the smallest subfield of F that contains all of the field L and all of the field M, right? Because the composite has to contain at least both of these. Okay, any questions? Okay, so now we start to get into this. So here's an important definition. So we've talked about in this notation, okay, sometimes I take a field like the rationals, and maybe I throw some other junk into it, right? Maybe I'm curious about what kind of field do I have when I take the rational numbers and I throw in I, and I throw in square root of 2, and I throw in one of the roots of the polynomial x to the fifth plus 2x plus 2, and then throw in e just for fun as well, right? Well, those elements that I'll give you are different. One of them is different from the other in the following sense. Definition. Let's okay, so let K be a little field, F be a field containing, let U be an element of the big field. We say that U is algebraic over K. Anybody know what it means for you to be algebraic over field? There you go. If U is a root of some polynomial. So if U is the root of some polynomial with coefficients in K, we say it's algebraic. I guess everything's the root of the zero polynomial. So let me put that in there. Be careful. If U is not algebraic, U is transcendental. I always feel like kind of a hippie when I write that, but yes, we say that U is transcendental if it's not algebraic. That is, it doesn't it's not the root of some polynomial coefficients in K. It's not zero. Can anybody name an element that's transcendental over Q? Right, these are kind of classic. If you've ever heard the folklore or seen a number theory course or whatever, right? Everybody's favorite examples are Q and E. E and pi, right? How many of you have heard that E is a transcendental number and pi is a transcendental number, right? At least you've probably heard that in folklore. That means that the roots of no polynomial. And the proofs of some of these can actually be kind of involved. By the way, so here's kind of a little aside here. How many complex numbers? Right? I mean, the complexes aren't really any bigger than the reals, right? Essentially. So, which are there more of? Transcendental numbers or algebraic numbers? Transcendental. How do you know that?
Show your class on infinity, and we talked about it.
Okay, gotcha.
But I don't remember why.
Okay, so basically speaking, if you look at the complex numbers that are algebraic over Q, right? Every one of them you can tie to its minimal polynomial. Like you could take radical 2 and tie it to x squared plus 2. And in fact, if you look at all algebraic numbers, they're just roots of all these polynomials. And that even includes the rationals themselves, because the rationals are the roots of linear polynomials, right? X minus Q. Now, I don't know much, but if I walk up to you on the street and give you a polynomial with rational coefficients, say of degree n, how many roots does that have? No more than n for sure, right? So how many polynomials are there over the rational numbers? There's countably many, right? Everybody agree? And for each of those countably many, you're only associating a finite number of roots. And a countable union of countable, and in this case finite sets, is a countable set. So if you look at the complex numbers that are actually algebraic, that forms a countable set. But the complex numbers, very big, uncountable. So this is the funny thing about being trapped in the human brain, right? Because if God were to pick a number truly at random, assuming that the divine can pick something truly at random, with probability essentially 1, a transcendental number will be selected. Right? But I challenge you out there in the audience, give me a number that is transcendental once I take pi and e off the table. And of course, the next thing I want you to do is prove it, right? It's difficult, right? So if you truly could select at random, then most numbers are transcendental, but are human limitations. If you ask your classroom to pick a number, they will pick an integer, right? And they'll probably pick an integer less than 10, right? So it's funny because most numbers are transcendental, but most of the ones that we're used to seeing and used to working for are in fact algebraic. Yeah. So here's actually kind of an interesting way. If you want to really construct a transcendental number, the best thing to do is not to look at pi or e, but to construct a strange decimal expansion that, like for example, that spreads out zeros, one pair of zeros, one prime number of zeros, or especially if you spread them out very fast, like spread them out growing like a factorial or something like that. And you could make uncountably many sequences that way, right? And this is why if there was something truly random, then you're probably not going to ever pick a rational number, right? Because imagine that you actually could pick every decimal in a decimal expansion, which is impossible. or we will assume some kind of divine thing, so you can go on forever and ever. What are the chances that decimal repeats? Right, I mean, no matter what pattern, it's very likely that, you know, at random, it's going to get screwed up later. Okay, so launched into philosophy there. If every element, the big one, F, is algebraic over K, then we say F is an algebraic extension. If even one element is transcendental, we say it's transcendental. And F, transcendental, let me clarify, transcendental over K, we say F, transcendental. So algebraic is a strong word, right? Algebraic means that everything's algebraic. Transcendental means at least one thing is not algebraic. So here's some examples. And the first one is of note, although it's trivial. Any field is algebraic over itself, right? Alpha in F is a root of X minus alpha. In a very silly way, any field is algebraic over itself. C is algebraic C is algebraic over R. I guess I should probably prove that. Let me sketch a quick proof. Right, I mean, if you've ever seen complex numbers, what's the first thing that ran down your throat is any complex number is the form A plus BI, right? Well, once you got that, we've totally got this thing licked because Z is a root of now, as written right there, this is not a polynomial over, well, each individual piece, neither one of these individual pieces is a polynomial over reals. However, if you multiply this thing out, you get that, which is actually so the element A plus BI is a root of this polynomial over R. So that's a really nifty example of an algebraic extension. However, so C is algebraic over R, but C is transcendental over Q. And my silly proof of this is either think of pi, think of E, or you can also think of that sort of informal proof I gave you that the elements, if you make a list of all possible algebraic or all elements that are algebraic over Q, you will get a countable set. This is uncountable. Whatever's left over has to be transcendental. Can anybody name a transcendental extension of C? Now C is of course algebraic over itself, but can you name a transcendental
Polynomial ring over C.
or an algebraic extension of C? Well, any extension of C's got to be one of the two, right? Because they're sort of mutually exclusive. There is no algebraic extension of C. There are plenty of transcendental extensions of C. Anybody know one? You're going to think I'm a cheater, pumpkin eater, or something like that. Just take rational functions over C. Right. It seems like cheating, right? Because you can take, in fact, you can do that with any field. In fact, if you have any field inside with rational functions, that will automatically be transcendental because the variable x does not satisfy any polynomial equation over f, right? You can't plug x in and have it come out as a root of a polynomial there. And in fact, I'm going to give you a theorem that basically shows you that if you're looking for transcendental, this thing right here, that's where you're going. So, without further ado, so I'm going to have K inside F fields and U in F transcendental over K. Right. Okay, so here F is an element of, U is an element of F that's transcendental. So certainly K is contained in KU and KU is contained in F because both K and U are contained in F. So KU is an intermediate field. This is actually isomorphic KX. This is actually isomorphic to rational functions in one variable over X, where I'm going to call this isomorphism B, where B restricted to K is the identity on K. Okay, so this is actually kind of wonderful because what this means, for example, is if you look at the smallest field containing Q and pi, and that's isomorphic to QX. The smallest field containing Q and E is isomorphic to QX. So that means that from this perspective, these things can't tell those transcendental elements apart, right? So when you look at Q adjoined with, when you look at the smallest field containing Q and E, it is isomorphic to the small field containing Q and pi. Okay, so let's prove this. Any element of Kx can be written as f of x and g of x, where f of x are polynomials, okay, but g of x not 0. And I mean that g is really not the identically equal to 0 polynomial. So consider consider p and I'm going to tell you how I'm going to work this. Now, I want to be a little bit sloppy here because the first thing that I really should do is I should make sure that this is well defined. But notice that Kx is UFD, and so any fraction here, if you could rewrite it another way, F1 over G1, you get the cross multiple terms are the same, and that translates to the quotients evaluated and U being the same. And there's an important point about that that's come up in a moment. So this is well defined. Notice that it's also clear that when I restrict to K, that means that, you know, I can consider g of x to be 1 and this should be a constant is just plugging U into a constant, which is just the identity. Okay. So I've got that taken care of. Now, let me point out that by definition, KU feed is on, right? Because the definition of the smallest field that contains K and U is just plugging into all possible rational functions as long as the denominator is not 0, right? G of transcendental, G of U is not 0, if G of X is not 0. Right? Because if G of U is 0, then U is algebraic. And of course, in a similar, so this is also another step into, this is the more substantial step in the well-definedness is the fact that this makes sense because it's impossible for that denominator to ever be 0 and have this blow up in our face. Okay, so it's on to its restriction down there. It's actually fairly clear that the way you plug in rational functions is just like polynomials. So this is actually a homomorphism. All we need is now it's 1-to-1. So suppose f of x over g of x is internal c, then f of u divided by g of u equals 0, which implies f of u is 0. This is the same as our well-defined in this part, which implies u is algebraic. So there we go. If you have a single transcendental element, then that's basically equal to rational functions of one variable.
How can we say that g of x equals 0 and we're getting this that it could? Are we thinking you want a different g of x?
Because this one, so I'm sorry.
So we're just saying that either implies u is algebraic or f is 0, right?
Right.
Okay, so are we assuming that this f of x over g of x is not 0 in the kernel?
We're assuming that, okay,
We're
right,
assuming
right.
it's not 0?
So, yeah, let me complete my thought
I mean, I guess it doesn't really matter.
here. So you have f of x over g of x in the kernel. This means this happens, which means f of u is 0. And so let me finish off better. Since u is algebraic, transcendental, this implies f of x must be the 0 polynomial, implying f of x over g of x is equal to 0. There, you're right. You're absolutely right. That's much better. Okay. So, now, as you might not be surprised about, things are like really kind of cooler when things are algebraic. Okay, and yeah, the fields and U and F algebraic. Okay. Number one. In this case, this is kind of interesting because what this means is the smallest subring of K, of F containing K and U is equal to the smallest subfield isomorphic. You could actually put an equals there. Number B, KU is isomorphic to KX mod F. The ideal generated by f of x, where f of x is minimal irreducible polynomial u over k of x. Say degree n. And let me also clarify that f of 0. That's what I mean by the minimum polynomial is use actually the root of that thing. And C, the degree of KU over K, which is the degree of KU, the same thing, is N, which is the degree of F, using my notation from the previous part. And D, every element of KU can be written uniquely in the form I equals 0 to n minus 1 of Ki dPi, where Ki and n is the degree of F. Again, using my notation from part B. Okay. Okay, so once I get part 1 done, I want to use that to kind of cascade out everything else. Let me point out first that note everybody agree with that? Because this is just polynomials in U, and this is rational functions in U. Really what this is the smallest ring containing KU, this is the smallest field. So we've got this. Since KU is the quotient field, K square bracket, it suffices to show that the square bracket is Q. And to this end, I am going to show that K square bracket is a field, and then everything else is going to tumble like dice because you're going to see all this show up in proof. So everything else after this will be a horizon, I think it's called. Okay, so how are we going to show the KU? Well, so to this end, such that okay. So this is just a collection of everything in K of X that kills U. This includes the 0 polynomial in kind of a silly way. Okay. Since KX is a PID, and I is non-zero, notice that I is not the 0 ideal because there's at least some polynomial that kills, some non-zero polynomial that kills U by the assumption that U is algebraic, right? Is generated by f of x for some irreducible. Why does it have to be irreducible? Let me point out that if this has to be a prime ideal, because if h of x, g of x, then I, then h of u, g of u, 0, which implies h of u equals 0, and g of u equals 0. Because after all, this equation is taking place in the field. Therefore, h of x or g of x so in fact, this shows that I is in fact a prime ideal and it's generated by some irreducible, which I'll call f of x. Notice that of course f of u must be 0 because of the fact that this lives in I. Now consider p and kx and u. And I think this is again the case of just plug in, right? Input, polynomial, output, which you get when you plug in u, which is of course an element in KU by definition. Notice that phi is clearly arbitrary. I hate saying clearly because someone really kind of a bit of a jerk, but by definition of what KU is, this is onto, right? Not one-to-one though. Phi is precisely 9, right? It's just all the crap that goes to 0 here. By definition, this is current. Therefore, K of x on I is isomorphic KU. But I is non-zero prime ideal of the PID. Hence, I is max. So KU is contained in 4 KU. Because KU is KX modulo maximal ideal, it's prime. Let's take a quick look at this before we kind of break for the day. This showed up in the previous proof. In fact, I had it with a square bracket, but now I know that that's equal to KU. And this is implicit in the proof, right? We'll talk about this. This follows from the proof as well, but I'll talk about the details of this next time. Any questions? Any questions? How about out there? Any questions? All right. Well, can we slide back to the last thing read? Oh, okay. Okay, so Jared's got questions.
I don't have a question. I needed to copy
Oh,
one more
Jared, do you have a
down.
question or are you just trying to write some stuff down?
I'm just trying to write the last thing down. Can you hear me?
No, I don't think you can hear from the Zoom.
Oh,
All right.
okay. Thanks.
Y'all okay? I'm not gonna raise the board until Jared gives me the green light.
Listen to it.